Hello. If anyone was a morning watcher, I apologize. Had some technical difficulties this morning, and was not able to get the thing started at 10:30. So, being that I repeat content in the evening, it will repeat here. I repeated this. I said this last time, or at least in some of my lectures. Eric noticed that one of the questions, one of the random answers was not generating a good root on it. When I went through, it wasn't actually doing it for every random version it had, but every now and again it would do a random k value that was wrong for the root. So I removed that question from the review and from the exams. So that's that. Emily, I will reply to your email this evening. I actually needed some more information, which I got today. I think that's everything I have administratively. We really are looking at two more classes. Today we're going to do section 5.3, 5.4, maybe a little bit of 5.5. 5.4 and 5.5 overlapped in my mind a lot. In fact, we can talk about everything and then dive in deeper to it in next class. This is a very deep subject. Exponentials and their inverses and the models that come out of them. For some reason, it always is at the end of classes like this. It's always the last thing covered, and usually always squeezed in into the last week and a half. And it seems to be, it's something that as you progress mathematically, you will always come back to exponentials, and particular exponential functions. And 5.7, I'm not doing 5.6. In fact, if you've noticed, I've avoided inequalities in general. There's a little bit of the concept of what an inequality was, but in general, I've avoided inequalities. Take what you will from that. You explore them, I think, a little bit more as you progress. But if you treat them like equalities, the big key is figuring out which side of the line of the function you're on. And I think as you use specific applications for it, especially with domains and ranges of functions coming out of calculus, I think it becomes a little more intuitive when you're looking at it in that context. But that said, today we are going to talk about exponential functions. Exponential functions. They are a class of functions, just like lines are a class of functions. So we had lines. Let me f of x is equal to mx plus b, and these values could change, making unique functions where the values of them and x changed. Then we had polynomial functions, which this is a particular type of polynomial. It's a first degree polynomial. We had quadratics, which were second degree polynomials that had particular behaviors. Well, exponential functions have some constant, so I'm going to put a big C as a constant here, some base to a power. It's some number that's multiplying a base to a power. And so their basic form is a base to a power. And we have used powers with specific numbers in them. We haven't let the power vary. And this creates a very interesting thing. And they're very popular models. In the last lecture, I talked about cells splitting as being a doubling model. In fact, the model that we will really talk about is we'll talk about growth or decay. I think dispersion is a word that tends to get used. They talk about how things move away from this initial value, this constant out front. So I want to actually classify what these things are. And so I'll use the book definition. I think the book is using A instead of B for base. So I'll change my language. It's C, some number, to a power, where A is greater than 0, and C is greater than 0. And so we're going to say this is a base A, and coefficient of C. All right, let's see if I can get one of these up here. I'm going to graph an exponential and look at some things that come from it, from things we should know about exponentials. And I think I'll use 2 to the x as my exponential. So let's come down here. Let's see if my graph, nope. Come here, make sure I get to my graph. There we go, there's my graph. Please, in the windows off to the side here, if I don't switch back to my graph, shout at me over here, right, in the chat, go. Say, hey Jeff, you are still on the graph. If it looks like I get stuck on it, I think I found the reason it's getting stuck. The button that lets me switch through what I can control is right next to the button in the software that clicks what you can view. And I think sometimes I tap it when I'm dragging my mouse across it, and that's why it's been slipping back and forth. But for right now, we should be seeing this graph of our function 2 to the power of x. And there's some things that are happening here that will be consistent for us in exponentials, no matter what the base is. In fact, for giggles, I'll put in 2 other bases. I'll put e to the x, because that's a common one we'll use, and 10 to the x. And so notice, these 3 separate functions are different bases to the power of x. The power varies. But they all have some similar features here. So I'm going to, again, just leave 2 showing. Now, where it crosses the y-axis, which is when x is 0, it's the number 1. Okay, all of these are number 1s. For every one of them, no matter what the base is. When the x value is 0, this function returns the value of 1. And I'm going to switch to the blackboard and back really quick here. So let's go there. So for all of these, b to the 0, oops, I'll again have to use the book's value, a to the 0 equals 1. So for exponential values, if you start at 0, no matter what the base is, you get 1. So that means when I write my function, f of x is equal to some constant times my base to the x. This part here, the a to the x, when x equals 0, is 1. X equals 0 means a to the x equals 1, which means the function at 0 has the value of c. And a lot of the times for this thing that's up front, it'll be like a sub naught or p sub naught, right? The amount at time equals 0, the population at time equals 0. It talks about the amount that this function is starting out with. Because when the x value is 0, this becomes 1, this constant in front usually represents some starting quantity. Let's go back and look at the graph again. So here on the graph, I start at 1. As x increases, I'm multiplying. Now, this is a function with a base of 2, which means my value of x is counting doubling times. When x equals 1, I am talking about the amount of time it has taken for my original amount to double. Right? Every space of 1 is double. So I start at 1, and when x equals 1, I've doubled to 2. If I move one more doubling time, which in this case is a space of 1, I'm up to 4. And if I move one more doubling time, I'm up to 8. And so for each progression of that doubling time, I'm remultiplied by my exponential. And so we have in our language this idea of things we'll call exponential growth. When we talk about things that are on exponential curves, they grow very steeply because their multiplications come about. Okay, I'm switching back over to the blackboard here. Definitely got the blackboard there. So, again, I'm going to use a doubling time. So I'm going to double. And so that means I'm looking at a function of a power of 2. And I'm just going to start out with one thing. So I'm going to put my c is going to equal 1. Let me give myself some more room here. So f x equals c, 2 to the x. And my c is going to equal with 1. I start with one thing, and I count how often it doubles. So at time equals 0, I have my one thing. And I'll think of human cells. Right? Whatever I'm measuring the time in x is, when 1 unit has passed, when I get to time 1, this has doubled. I now have 2 things. When I get to whatever my doubling time is, one more, when I go from 1 to 2, this quantity has doubled, and I now have 4 things. Because each thing in my model can make a copy of itself. Right? Cell growth is kind of nice for that. I think hopefully we've all seen the videos of cells splitting, and each cell makes a copy of itself, and so each layer doubles. And so that's what this function does, with the base being 2. Now if I change my base, let's say, I'll go to bright green here, g of x equals 10 to the x, and I'll put c out in front of it, but I'll still start with c equals 1. So when x is 0, I still have one thing. But in the length of one doubling time, this will create 10 copies of itself. Right. And so the base is really determined by different laws coming through. Now, these class of functions are all different, right? 2 to the x is different than 10 to the x, which is different than 3 to the x, which is different than e to the x. Right. So these functions have a whole bunch of different behavior. But because the variable here is free to have mathematics around it, we have a tendency in our lives to only use these 3, 2, 10, and e. And you're going to find that my discussion on these is really going to narrow around the last 2, 10 and e, because we're going to be able to modify what's in our exponent so that any one of these will look like any of the others. And it's what comes out of them. So we have our new function here. It's some base to a power, and we have to manipulate that quantity. Whatever comes out of that will multiply the c value in the front. All right, so let's describe this function fully. Again, I'm going to go to the graph here to do that. All right, so notice this function starts at negative infinity and goes off to positive infinity. So its domain is all real numbers. I can take any base to a power of any real number. Its range, well, if I go down here, I never get to 0. If I go down the negative x side, I never get to 0. And if I go to the positive x side, I go off to infinity. So if I were to write this in my domain notation, all exponential functions have a domain of x, is an element of all real numbers with no restrictions. And the range is x is an element of all real numbers, right? And again, this is the range. We technically be talking about our function value that pops out of it, such that it is greater than 0. Never equals 0. All right. This becomes important for what we can do with these functions. We know the domain and range of these functions coming out. So if we do interval notation, right? The domain, your book dances between these two notations. I think there were 2 different authors between the chapters. But what I want really clear here is it can't be 0. The graph is continuous. There's no breaks in it, and it's asymptotic to the x-axis. F is 1 to 1, so we can have an inverse for this. And that's going to be the important part we go to. All right, so this function is invertible, and there's an inverse. So we can undo this idea of putting things to a power. And so notice how we're using all the language we use to functions. We're using the things we developed from polynomials to talk about these new things. I want to add one other thing to this, and then we're going to look at its inverse before I do any particular models. And we'll look at some examples of what we can do with these functions without the models, just mathematically. So I'm going to switch over to using e to the x, because I like e. It's a nice exponential, and I've been using it a lot. And we're going to find what this number e is. It's very similar to pi. And pi is a constant number, e is a constant number, 2.78-ish, I think, or 718 for e. But e is very important, and so I'm just going to start talking about it and define it as we move further. So notice x is positive here. And a lot of the times when we talk about exponential models, the exponent is time. And we're talking about how time increases. So we tend not to talk about time less than 0. So I'm going to limit my values here to be greater than or equal to 0. So if we're talking about 0 being the starting time, these functions start at 1 and increase when x is positive. And so the models that we're going to use where things grow or get bigger, our variable upstairs is positive. But if you take the exact same base and take it to the negative x, I get this purple value, which is decreasing. And so we're going to call this decay. So as I switch over to the blackboard, how we are going to interact with these, we will have a tendency for two descriptions. We'll have exponential growth and exponential decay. And in growth models, I have some starting amount. So some starting amount, that's what the sub-zero will be here. Whatever my base is, and for this I'm going to use E. A constant times my variable. Now over here I put X, so it'll be X. A lot of the times it'll be T, because we'll be talking about time. K measures the growth rate. And is greater than 0. All right, over here, exponential decay has some starting amount, my base, negative k to the x. And k, in this case, measures the decay rate. And k is greater than 0. Because we need this negative exponent to force that exponential to decay. Now, we can talk about f of x equals some amount e to the k x, and we talk about the full function with its negative side and its positive side. But because this is usually time, we usually only talk about this side of the function. And you'll see that when building the models that we come through. But the behavior of the function is such that it should be 1-to-1. It's asymptotic to the x-axis. It goes off towards infinity, but there's no humps in it. There's no changing back. And so it passes a horizontal line test as long as a vertical test. That means there should be something that I can reverse this. And I'm going to show you what I mean by this. I'm going to use 2 because we can walk the function down nicely. So if f of x is equal to 2 to the x, then I can make a table of values. I can make my f of x values and my x values. And I'll go 0, 1, 2, 3, 4, 5, 6. So 2 to the 0 is 1, right? Plopping this value in, getting the output. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. 2 to the fifth is 32. 2 to the sixth is 64. So if I plop in x, I get my function out. So there should be some way that if I start with my x values, so if I start by dropping in these 1, 2, 4, 8, 16, 32, and 64, there should be some function, some inverse function that gives me 0, 1, 2, 3, 4, 5, and 6. I should be able to invert my exponentials. I should be able to use the fact that they're 1-to-1 and invert the process. Just like I can invert additions and I can invert subtractions, there should be a function that inverts this. And so we can go, all right, well, 6, well, go back one, 8 equals 2 to the what? Right, that's what we would be doing to invert this. It was 8 equals 2 to the what? And we'd find a way to answer. Well, when I inverted f of x equals 3x plus 1, right? I'll do my steps of inversion here. All right, so how did we find an inverse? I let this equal y equals 3x plus 1. I switched x and y, and then I solved for y. And there was my inverse. Right. So here, if this function is y equals 2 of x, I want to find my inverse. So I switch x and y, and I solve for y. But we're stuck. And mathematicians were stuck. We don't have a mathematical operation that pulls this y down. I can't undo 2 to the yth. I don't have an anti-yth function. I don't have an operator that pulls this down. So mathematicians had to go, well, what does it mean to be one-to-one? And a lot of the things we learned about inverses and making inverses and the graphing of inverses and switching domains and range came from this problem of how do we reverse exponential growth? How do we reverse an exponential function? And so what mathematicians did is they said, okay, let's look at our exponential function again. I'll do this in blue. Let's look at f of x equals some base to a power. And its domain was from negative infinity to positive infinity, and its range was, but not including 0, from 0 to infinity. And they said, well, my inverse function is going to have a domain from 0 to infinity and a range from negative infinity to infinity. These are going to swap. They're also going to reflect across the axis y equals x. So let's go over to our graph here. Let me get rid of the e to the negative x. I'll just keep the e to the x here. I'll make the overall function. And remember, our inverses had to mirror that line y equals x. And so what mathematicians did is they invented a function called a logarithm. And a logarithm's job was to take the output from an exponential and make it the input of the logarithm. Take the input of the exponential and make it the output of the logarithm. And they actually did this with tables. I have here and in my office some old math books. And before computers came across, people used slide rules, and logarithms and exponentials helped in using slide rules. But to do that, you had to look up the value of the functions. And so what they would do is they'd calculate what is 2 to the 4.2. And they'd calculate it out and they'd write it down on the table. And then in the table they'd go, well, the logarithm base 2 of this answer is 4.2. And so they would make tables just like when we make an XY table. They made tables for these numbers and they calculated them to precision, and then they would publish the tables. And up until the 70s, even early 80s, 1980s, you could still buy these tables. You can still buy tables now for many different functions, but before pocket calculators, I think about 75, 76, HP made the first handheld calculator that could do trigonometric functions, and that was about $500. Bright red LEDs on it, and usually only engineers had them. So before those things became popular or even available, these tables were made to reverse these. And so they took all the answers from here and they made them the input from here. And they took all the input from here and made it the answers from here, which is why we inverted functions. And so they make this function called the logarithm, which reverts exponential decay. So let's look at logarithms. Now, one of the things about this, I'm switching back over to the blackboard here. One of the things about this is there are many different bases. There's an infinite amount of these functions. Whoops, back to the blackboard. There's an infinite amount of these functions. I can have a can be any number greater than 1. Right? Actually, it can be any number greater than 0. A equals 1 is not interesting. Right? It's 1 times 1 times 1 times 1 is still 1. So mathematicians focused on numbers that were very common to come across. So they focused on 10 to a power, e to a power, and 2 to a power. And 2 actually, I think biologists keep a hold of that because doubling times are really important in how they measure things. And so this is kept. So to do that, they made tables of these numbers, and this was called the inverse function of this. Its inverse is called the common logarithm, and it was written as log x equals y. This was called the natural logarithm. And e is considered the base of natural numbers. Again, we're getting there. I'm going to show a model where e pops out. E is an important number. Probably as important as pi. Maybe not as important as 1, but really close to it. And so natural logarithms are written as natural logarithm. And of course, this y could be a function. I could say f of x is the log of x. Over here, I could see f of x is the natural log of x. Right? I'm writing it in x equals y format. And this one had no special name. It gets used a lot. And so it would be the log base 2. And so the base gets written here. So the general unnamed version of a logarithm, logarithms with names, are common log and natural log. The unnamed version is log base x to y. And so you state the base that you're using. And the base relates to the base of its inverse function. The exponential that made that logarithm. The exponential they used to make the table of values for that logarithm. Again, because they had to publish books of these, because they had to produce tables to work with these values, they really focused on these two, the common log and the natural log. And so a lot of our mathematical tables are done around it. Now E, this thing here, this base here, because this number is so important, you'll find I'll have a preference towards talking for it. Now, on your calculators, as I go to grab mine, these keys have functionality. You do not get, on most calculators, a log base x key. You don't get that. On some of the Timex ones, you can go into math mode and you can specify the log and the base. It's a lot of keystrokes, but on the keypads, they will have a log key and an ln key. And usually above the log key is 10 to the x, and above the ln key is the e to the x exponential function. So you can go right to those keys. TI-89s don't have the log base 10s. Everything is ln's on them. But I think every other calculator has these two keys to get to these functions. They're that useful. And so we have a way of reversing a logarithm. So if I look at what I had before, if I had a function of x, but mathematicians had to make up the function, and that function's job is to reverse things. So if I have 2 to the x, and I'll make my little table of values. And so 0, 1, 2, 3, and so on. 0, 1, 2, 3. 0, if I put 0 into f of x, I get 1. If I put 1 into f of x, I get 2. If I put 2 into f of x, I get 4. If I put 3, I get an 8. Its inverse function, which I'll just say g of x, equals log base 2 of x. If I put 1 into here, 0 pops back out. Oops, this is g of x. So writing on this tablet is killing my hands slowly. So if I put 1 into here, I get 0 back out. If I put 2 into here, I get 1 back out. If I put 4 into here, I get 3 back out. So this function reverses this function. All right, so we have our landscape now, and we're going to need to see what we can do with these functions and what rules can come out of these functions. Well, these functions are related to inverses, and so their properties hold some value. So, how much room do I have? Good, I'm good with room here. So I'm going to put my exponential functions over here. And I'm not going to care what my base is right now. I'm just talking about the general behavior of these functions. We will dive into particular functions when we build specific models. And I'll put my logarithms over here. And logarithmic functions, I think is how we say it. Logarithmic functions. And so I can write this in the form of y equals b to the x. Its opposite, or logarithm, is log base b and I want to say this in a way that relates to the other ones. Let me think for a second here. Log base b of x is equal to y. These x and y's are inverses. So right now, these numbers are inverses. So this x domain is not the same as this x domain here. It's just how we talk about these functions. We'll make a mapping back and forth of these when we choose specific ones. All right, well, there are some things and rules that we had from exponents that we started the semester with that are going to help us with these functions. So b to the 0 is always 1. That means log of base b of 1 I just dropped my note paper down here and I can't reach it. Hold on 2 seconds here. I'm saying this. So the log base b of my output of 1 equals 0. Logs cannot have 0 in their functions. Right? 0 for a log is undefined. It's like trying to divide by 0 in this case. But log base 1 is equal to 0 because that's how you get the inverse here. All right. Any number to the first power is b again. So the log of some base to itself is 1. All right, so let's look at an example here. If I'm coming from, if my function is 10 to the first, or 10 to the 0 here, sorry, that gives me 1. So my log base 10 of 1 is equal to 0. It lets me go backwards or forwards. These properties are related. Notice, I want to say about 4 or 5 weeks ago, I repeat this. I repeat this in a lot of classes. And I probably repeated it more than just 4 or 5 weeks ago. Is when we define functions, looking at where 0 and 1 are very important for us. And in these cases, the 1 and 0s, what is happening with 1 and 0 are helpful for us. All right. Then there are some neat properties that happen when we had some things that happened with our exponents. And so the rules of exponents, if I have the same base and I'm multiplying them, I added the exponents. If I have a logarithm to the same base of m, and I add to it another logarithm of the same base, I can add their inputs. Now this left-hand side we have done. I'm showing you what the logarithms do. Because these are inverse functions, these are related. And so I want to put these rules together so that we're used to seeing them together. Well, we had, if we divided with the same base, it became a subtraction. So if I have a logarithm with the same base and I'm subtracting, it becomes a division. And we had, if we did an exponent to a power, we multiplied. Here, if I have a log to a power, I multiply out front. And so this power can come out front. So because these functions are inverse to each other, these rules that we had for exponents have a similar set of rules for logarithms. And these are called the properties of logarithms. And they help us manipulate them. So we now have these two classes of functions. One that are inverses of each other. They can undo each other. They can help us go back and forth with each other. And that's going to help us when we do our exponential models. The logarithms in their own right have their own models that come out of logarithms. but they're also useful in letting us work our way through. Now, one thing that comes out of, because these are inversions of each other, these are inverse functions of each other. So we had this rule. If I took a function and composed it of its inverse, I would get x. And if I compose the inverse of the function, I would get x back. That's how we made, that's how we proved functions were invertible. Well, then if I take log base b and put into it b to the x, that's its inverse, I get x back out. And if I take b to the power of log base b to the x, I get x back out. Because that is the inverse of the exponential function. And this is the secret sauce. We now have a rule that comes from this inversion. That, notice what it did. I had something to a power here, and I had something to a power here. But by doing this, my answer has no powers in it. And this is what mathematicians had to invent. We were stuck with exponentials, and we have these things upstairs in the exponentials, but we couldn't get anything downstairs from them. So they had to invent the logarithm. And they literally just said, hey, all the answers from these things will make the input to this other thing. And all the input from the original things will make the answers. And so they made, and they just built tables of them and used them. And so these are the rules that I'm going to keep coming back to and coming back to. And we're going to build an understanding of these rules over today's lecture and next week's lecture. But I want to start with all the rules on the table. And so we're going to keep coming back to them. All right. Now, again, I have a bias towards E as a base for logarithms. It's because it comes out of many differential equations. So I'm going to show you a couple models with exponentials, and I'm going to show you where we got E from, and then I'm going to build in using logarithms to undo E. It's coming through. So I'm just going to do a quick recap of where we are as I start moving into some particular models on this here. So we have a function that is some base to a power. It's called an exponential. That graphs with positive coefficients in front of x, it graphs as a growth. If I have negative coefficients in x, it graphs as a decay. And I didn't draw my decay here, so let me draw my decay over here. Write it by decay. All right, that would be e to the negative k of x. This is a decay. And so exponentials model growth and decay very well. And they're the functions we tend to use. A decay from starting point going down, and a growth from starting point rising. Exponentials can accept any real number as their input, but they spit out numbers that never quite reach zero and go off towards infinity. They're always positive. Well, looking at them, they're invertible. They pass the horizontal line test, they pass the vertical test. They should be one-to-one. So we need some function to invert them. And we try mathematically, we have no operators in existence that let us invert these functions. So mathematicians go, well, if I want an inverse, I swap the range and domain over. So why don't we just write down every value we ever get, and we'll make that the input for the inverse, and the output will be the input we started with for the exponential. And for centuries, they published little tables of books where you could look up the value of what they called logarithms. And so logarithms are a collection of functions that are related to exponentials. So here I have 3 exponentials, and I have their related logarithms. Now, because the base in exponentials, I have an infinite amount to choose from, but I only have a finite amount of trees to make paper to print tables of books from, mathematicians decided to focus on particular bases. And base 10, because our number system is in base 10, was very common. And that's called the common log. And it usually gets written as log. Now, there are some old mathematical textbooks where log means whatever logarithm the mathematician is thinking of. Very annoying. Wolfram Alpha is guilty of using log as the natural log. But most modern text, log means that it's a log for base 10 exponential. And it's the inverse function. It reverses taking 10 to the power of something. Natural logarithms have a base of e, and their job is to be the inverse of e to something. Now, again, my bias to e to something, it is e exponential as a function. The number e is extremely useful. It has some mathematical properties that make it appear as solutions to differential equations fairly easily for us. So a lot of models you get will use this as their base function because of its prevalence. And then you can have any base for your exponential. 2 is quite common because doubling times are very popular. 1/2 is also popular. You could have 1/2 to the x for talking about half-lives of things. And so there you would talk about the logarithm having a base. And I have already set you up for a problem that we'll look at probably in the middle of the second half of tonight, where your calculator only has 2 keys. It has log base e and log base 10. How do you calculate log base 2 with a calculator? And we're going to put all these rules together to do that. But so we've invented this thing that reverses exponentials. And so we look at it and we swap the domain and range. And so some things we know about logarithms that we should get from looking at them is its domain is always positive values. So going into x here, I can only put things greater than 0. If I put 0 in, I'll get an error, just like trying to divide by 0, because logarithms are not defined at 0. And so they're all positive values going in. I can't put a negative number into a logarithm. So a lot of times you'll see absolute values to enforce a positive value comes out of it. And then in the range comes out all real numbers. And the secret part of this, if I'm going to switch over to the graph here, is if we look at this being right at the logarithm of 1, numbers smaller than 1 going into the log give me my negative numbers. And logarithms where the numbers are bigger than 1 give me my positive numbers. All right, so there's 1, 0. And so what ends up happening if I'm throwing a number into a logarithm and I'm putting a fraction or a decimal in, I'm getting a negative answer. The converse is true. If I'm seeing negative answers coming out of logarithms, I know fractional values are coming out. And that's from the fact here that at 0, I have growth. Below 0, I have decay, or I'm getting smaller. And so those inverse operations between the exponential and the logarithm give us a sense of what this logarithm's doing. Okay, back to the blackboard bit. right, so we've created this function, and well, what does this function do? It reverses the exponential. Well, let's look at some rules we know about exponentials. We applied these rules for the bases when we knew what the values were, right? We had x squared times x to the third, and we knew that would be x to the fifth. Well, now we can have 2 to the x times 2 to the 3x. Well, that's going to give me 2 to the 4x. That's what these rules do. But the logarithms, being inverses, have a very similar relationship with these rules. And these properties of exponentials and logs we are going to come back to over and over again. And so I learned them kind of as pairs because they're inverse functions. They sit with each other. Just like whenever you saw me write PEMDAS up there, I would write addition and subtraction on the same line. I'd write multiplication and division on the same line. And I'd write exponents and their roots on the same line because they were invertible operations. I do the same thing when I think of exponentials. I put the exponential and the logarithm there so that they're related, and these rules are related. All right, and so that's what we did. Oh, and because they're inverse functions, and the secret sauce, the magic we're going to use, right, is if I take a log and I put into it the exponential that it's inverse, I get just x out. And if I take an exponential to some power and I put into it the log with the same base, I get x back out. And we're going to find that's the trick we're going to use to get things out of the exponent for us. To get things out where we can clear them. So that's a recap of where we're at. We have this idea that I can put variables into the exponents. But right out of the gate, there's a difficulty. I can't get them back down. And so we have to invent the logarithms. So this is the landscape we're in. And this is the landscape we're going to build upon here. All right, let me clear this. And we'll look at some particular exponential models and work our way through them and what we can do with them. Hey, that worked. All right, so exponential growth and decay tends to be something that happens quite often. And so I'm going to look at a couple of exponential functions. And I'm actually going to do two common, do a population growth, and I'm going to do it using doubling times. And then I'm going to use it using doubling times with a different base than 2. And then I'm going to do radioactive decay, which talks about half-lives. And I'm going to use it then using a base that isn't one half. So I want to get a good population model. I think it's in this notebook. There's my logs. I knocked over the paper, I knocked over my notes, but I was getting back to them. There we go. And there's exponential doubling times. Using exponentials graphing. Did that. Yes, here we go. Wanted to make sure I had. Okay, so the problem we're going to look at and solve using an exponential growth model is we could have some initial population. And so we'll say a town has a population of 16,400. Right, at some time. I'm not going to give it a year or do any of the year calculation. We'll just say this is our starting time. In fact, mathematically, we'll say that's when time equals 0. And I'll call this the starting population, so I'll even put it into the variable P naught. Population at the starting time is 16,400. And in years, it is predicted to double. So find a function for this. And find the population. In 50 years. So this is really how we see exponential problems. We have something that's doubling or it's growing and it has an exponential growth. A little idea on why populations can be seen as growth models. I've been trying to avoid, because I previously, before coming to the Mount, I worked for the biological science department at Southern Vermont College, and literally there were like 4 types of problems I do. For the rad tech students, I do radioactive decay problems. For the biological sciences, I do population growth rates and logistic curves, which is a combination of the growth and decay rate in the population. But I also do disease spreading rates for the microbiologist. And a lot of what we're talking about right now is in the news a lot. We have logarithmic graphs. Because these things are growing so fast, you can't put them on graphs normally, so you make a log scale graph. And so each line on the graph, instead of going up by 1, it goes up by a power of 10. Seen a lot of those floating around on Facebook, actually, and having to explain log graphs to people, which is okay. That's what mathematicians do. But these rates of growth and these variables we look at in doubling times and rate values, they basically refer to, and I'm going to just talk about population growing. If I have a population in a town, every pair of people in the town, right? But every person in the town has a probability of creating a new person through meeting someone, going through the required biological process to make another person, and then successfully going through it. And then in those cloned people have the ability to do the same thing. And so the population increases itself. And because it's a multiplicative, right? Biblically, go forth and multiply, right? Exponentials are multiplying, right? This is literally the mathematics of go forth and multiply. So we're looking at how often we can double the population. It doesn't mean populations double. Everyone makes 2 copies of themselves, right? But you can measure the amount of time it takes a population to double. And because the dynamics that drive that for any collection of people are the same, that group's going to double at the same rate. And so we look at doubling times. And so I can talk about my population now in terms of doubling times. I can say the overall population as some function of time is going to be 2. Whoops. It's going to be whatever the original population was. P to the 0. My initial population. And it's going to double. And it doubles every 20 years. And so what we have to do is we have to put T divided by 20. That's what we do with the doubling time. Well, let's test this, right? All right. So, doubling this, let me do this in pink. If I double this, that's 32,800, right? So let's try this function. If we double in 20 years, in 20 years, my population should be 32,800. So I'll come down here and I'll go P of 20. So I take my initial 16,400 and I take it of 2 to 20 divided by 20. Well, 20 divided by 20 is 1. 2 to the 1 is 2. 2 times 16,400 is 32,800. So we've made an exponential growth model. And we've done it off of this idea of the doubling time. All right, well, let's use it to predict the future. Da-da! I'm sorry. It's just mathematics is the tools we use to make future predictions. Based off of the models we use. Models are only so useful. But we do okay. So we want to know what happens in 50 years. So I will put in my 16,400 initial. And I will multiply that by 2 to the 50 divided by 20. Well, I'm definitely going to need my calculator on this here. So 16,400 times 2 to the power of 50 divided by 20. And I get 92,772.4. I have a tendency when dealing with population things to always round up. Unless times are really, really large for a unit of 1 in that 50, before that 50 years is over, right? Before the 51st year is over, I'm gonna get the rest of that decimal of a person. But that's just the tendency of how I answer the word problems dealing with these. So this is what we mean by an exponential model, and this is how they come in useful. There are definitely many, many systems that have growth rates that are predictable over a unit of time. And the unit of time that manages them can define how we can make predictions large scale into the future. And city plannings use doubling rates a lot, and growth and decay rates. We will look deeper into a thing called a logistic curve that takes into the account how quickly people are being born versus how quickly people are leaving. And you get a deeper curve called a logistic curve. But this is how exponential models work, and this is a growth rate. All right, I'm going to look at a decay rate here. So phosphorus 32p. So atoms have really large nuclei on some of them. Phosphorus is one. And so I have a chunk of phosphorus with all these protons and neutrons inside of it. Now, the quantum mechanics and the forces that hold these atomic nuclei together randomly split. And I get the nuclei break apart, giving me different atoms. And so phosphorus 32 decays such that half of the stuff changes in 14 days. And so in populations, we talked about doubling times. In decays, we tend to talk about half-lives. Tend to talk about how long it takes for half of the stuff to go away. for phosphorus 32, what does it break into here? I have to look at it. Sulfur. It decays into sulfur 32 and beta particles. And so, sorry, I had to look that up. And so this will break down into sulfur 32 and beta particles. And so if I had a chunk, if I had some amount, we'll say 50 grams of phosphorus 32, 14 days later, I would only have 25 grams left. And then I would have a chunk of sulfur 32, and there'd be some radiation that's released, right? And so this is called radioactive decay. So I can make a model where I have some initial amount of my substance, which in this case will be 50 grams. And my half-life is 14 days. So I can write a function of the amount of stuff I have is the amount of stuff I start with. And I'm going to take 1/2 of it. Well, time divided by 14 days. If I'm doing t in time, or days, t in days in this case. Same as we did the population model, except I'm halving. So the only thing I've changed is my base. And I've changed my base over the mathematical operation I was doing. So when I was doubling, I'm multiplying by 2, multiplying 2, multiplying by 2. But when I'm halving here, I'm multiplying by halves. All right, so let's see if this works for us here. I'll try to switch back to purple. So if I have 14 days and I start with 50 grams, I have half of 14 divided by 14. I'm sorry, half to the power of 14 divided by 14. So that's 1. 1/2 to the first power is 1/2. That's 25 grams. So it does what it says on the tin. It calculates the half-life well. Well, how long would it take, or not how long would it take, that's the question I'm going to go to next once we get back. But how much would I have left after a month? And so we use 30 days. Go back to yellow here. A of 30 equals 50 grams. We're going to have 1/2 of 30 over 14. So you see how our exponential model, we're tracking the motion through, and in this case time, moving through the exponent. And it's our multiplications going across the exponent. And these decay and growth rates are the most common exponential models that we have. So 50 times, sorry, grab my calculator here, 1/2 to the power of 30 divided by 14. And I would only have 11.32 grams left. And so that's how decays work. Calculator is going to be your friend on exponential models. We're going to be dealing with mathematics that create large decimal values and decimal representations, or have large exponent values on them, because the work is in the exponent. Doing growth and decay by hand, it can be painful. All right. I'm going to do one more thing somewhere around 7:30. We'll take a short break. We'll come back around 8-ish again. And this is, as far as my crazy, keep to myself political nuts that I am coming out, I'm going to make a statement here that's completely sarcastic, yet in a way, there's a hint to it being a mathematician. I'm going to give you the greatest gift bankers gave the human race. This mathematical function we're going to look at was a question of bankers, and in the 1600s, the bankers came up with a solution to this problem that gave us the number E. And then in Euler, Gauss, Riemann studied this number, and it revolutionized mathematics. And so what I'm going to actually show you is Euler's identity. So E is a number that if I raise it to the power of the imaginary unit times pi, and I add 1 to it, I get 0. Now this is not how the bankers found it, but this is how important this number is in the nature of things, and how this pops out behind things. So this number was found by bankers. And why mathematicians really like this is, remember when I talk about functions, I say we need 0 and 1 to find how the function works. I told us that I was very important for figuring out when things weren't real numbers. And pi and E are two other constants that are really important. I think just the fact that we have a national Pi Day or an international Pi Day to celebrate pi should help point that out. And so I'm going to show you what the number E is and how E works. But I'm going to show you where it came from. And it came from a banking problem. And so there is a banking problem where you can have some amount of money in your account that's your principal, I'll just put the whole equation here first and explain it. And I'm going to explain it while I write it. This is called the compound interest formula. Yep, show. And what happens is the amount of money I have in my bank is the amount of money I've started with, which is called principal. So A is the amount in the account. I'll rhyme today. P was the principal, the starting amount, initial investment, term of the loan. R is the interest rate over a period of time. Normally we do yearly interest rates, right? In fact, saving money right now in the bank, the interest rates are really low. I think it's sub %. When I was a kid, it was usually around 4 or 5%. And it's become to the point where savings doesn't accrue as much interest as it used to. Now, banks loaning you money use this calculation in reverse. The amount you owe them is the principal multiplied by the rate in the equation. So normally this is the interest rate per year. N is the number of times the interest is compounded. And T is the time that has passed. Now, compounded is an interesting thing. I never understood this. In fact, I'm horrible with money. You can tell just by the way I dress. Right? But compounding interest is when the bank decides the percentage they're going to give you, they're going to put back in. So let's say I have $100 and I have 1% interest on it yearly. At the end of 1 year, the bank gives me $1 and puts it back in. That means they're compounding it annually. Every year they take what is owed me and put that $1 in. So at the end of the year I would have $101. Well, the more often I compound it, the quicker my bank account grows. In fact, it actually starts looking like exponential growth, but that's a different story. Not quite exponential. It has a growth curve. We'll look at it. So if I compound monthly, every month they calculate the amount of interest. That would be a month's worth. So that 1% would be a twelfth of $1. And they'd put that back in. But now my bank account has more money, so when they go to calculate it again, they can't calculate it against the $100 I put in. They have to calculate it against this $100 and 8.5 cents, right? $100 and 8.5 cents. Sorry, not working that out. And so that's what this formula represents. And this is going somewhere. This is really going somewhere. So the more often they compound the interest, the quicker my money grows. And so that's the compound interest problem. Well, it would be really, really nice if they compounded it every day. Let's look at that and see if I have one here. Yes, they have this. So if I put in a principal investment of $1 at a rate of 1%. Oh no, this isn't at a rate of 1%. This is a rate at 100%. So this is my of 100%. I apologize. And so that means R equals 1. So that means every year my money would double. Well, if I compound it annually, at the end of 1 year, I would have $2. Right? So let me make a chart here. I want to put this in this terms. So I have A equals what I invest initially plus my rate over the number of times it's compounded times the number of time. And so what I'm going to look at is I'm going to put in $1 for P, but I have a great interest rate. My rate is 100%. So my money doubles every year. And so I'm going to make a chart of how often I compound it and how much money I get if T equals 1 year, what I'll get at the end of the year. So if I only compound it once a year, I get $2. If I compound it every month, so I put in $1, 1 plus 1 divided by 12, all to the power of 12 times 1, I would get $2.61. If I compound it daily, which is 365 times a year, so I would get 1 times 1 plus 1 divided by 365 times 365 times 1. I would get $2.71. And so banks were like, hey, what if I compounded every second? Which means that I would compound it 31,000 or 31,536,000 times in a year. And you go, oh, well, if we compound it every second, we get 2.718. And the question became, what if we compounded it continuously? Which meant that this n number would work its way towards infinity. And that's what the mathematicians worked out. And what happened is if all of these numbers are 1, if the rate is 1 and this is 1. And n approaches infinity. So we're looking at 1 plus 1 over n to n approaching infinity. The number that pops out of here is called e. And it's approximately, it has a value, I think the book does it to 12 decimal places. Yeah. 2.71828282846. And it's like pi. It repeats it goes on forever. It never repeats. So it's a transcendental number. It goes on and on and on. But it came from this idea from bankers of what was the most amount we could compound this to get the most back. And so compounding continuously. Well, what ends up happening is reality does that. Functions in reality compound. Their changes happen an infinite amount of times in a small space. Things approach infinity or approach an infinite amount of times a lot. And so E ends up popping up out of calculus left and right. And so this number became very useful. And so we use it as a base. And it came out of that compound interest formula as a base. All right, so I've covered most of the things in the exponentials and the early models, showing where the compound interest came from to give E. We're going to take a short break. We'll be back around 8. I'll send out the new link. And what we're going to do is we're going to use, we have a growth and decay model, and I did them using a base that was logical for the base. What I'm going to do is I'm going to use these logarithms and the rules of logarithms to show you how we can use them with your calculator. We're going to get through the limitation that we can have an infinite amount of bases, and so I really want to focus on functions of only 3 bases, and that's going to be our focus coming back. In fact, I'll even say those 2 because they're the keys on my calculator. So we'll take a half hour from 7:30 to 8:30. I'll send a new link out in 2 shakes. Everyone stretch. Kind of look at your textbook. Scream if you need anything, and the new link will come back up shortly. All right. See you in a bit.